Hi everyone, and welcome to week 8 of Introduction to Causal Inference. In this week, we'll be covering instrumental variables. As usual, if you have any questions or comments throughout the course of the lecture, go ahead and leave those in the YouTube comments down below. As we've seen, if we don't have any unobserved confounding, we can easily identify causal effects. For example, we can do that with the backdoor adjustment. However, what if we have some unobserved confounder? So we depict that as U here with the dashed border around the variable to let you know that it's unobserved. And it's perfectly reasonable to think that we might have some unobserved confounding when we're doing observational studies, because we very well might not have access to some confounders. So we need to know what to do in that setting where we have unobserved confounding, and we've seen a few different techniques for what we can do. For example, in week 5, we saw that if we have the front door criterion satisfied, then we can use the front door adjustment. Similarly, we saw that we have identifiability if we have the unconfounded children criterion satisfied. The backdoor criterion and the front door criterion are special cases of the unconfounded children criterion, so it's more general. And this unconfounded children criterion isn't a necessary condition, so we can also get identifiability via some fancy application of the rules of due calculus, since we saw that any identifiable causal estimand can be identified with a sequence of applications of the rules of due calculus. And that's all stuff we saw in week 5 for identifying a specific point for the causal effect. In week 7, we also saw set identification. So that's where we tried to get an upper bound and a lower bound on some causal effect, giving us an interval that the causal effect must lie in rather than giving us a specific point that the causal effect must be. And then we also saw sensitivity analysis, which is where we try to quantify how different the true causal effect would be from our estimate, where we adjust for observed confounders based on the postulated strength of the unobserved confounding. Right, so this is where we got those bias curves depending on how strong the unobserved confounding is. And instrumental variables are another technique for addressing unobserved confounding. That's what we'll see in this lecture. This is the general structure to have in mind for an instrumental variable z here. The intuition is that z will cause some changes in t, which will then translate to some changes in y. And the hope is that we'll hopefully be able to identify some causal effect using that variation in t that's specific to z, that's not dependent on u. Here's the outline of this lecture. We'll first define what an instrument is. Then we'll emphasize that there is no nonparametric identification of the average treatment effect with instrumental variables. Then we'll warm up with showing some identification in a simple linear setting. But because it's a linear setting, it's not super satisfying. We might want more general identification where we don't have sort of linear parametric assumptions. So then we'll move to nonparametric identification, but it's not of the ATE, it's of a different estimand, which is called the local ATE. And then finally, I'll point you to some settings where you can get identification of the average treatment effect, where you have more flexible assumptions than the sort of linear parametric form. All right, so let's move into the first section. What is an instrument? There are a few different assumptions that an instrumental variable or an instrument must satisfy in order to qualify as an instrument. The first is that z has a causal effect on t. That corresponds to this edge circled in blue here. And this assumption is sometimes referred to as relevance. The instrument is relevant to the treatment here, in that it's a cause of the treatment. Then the second assumption that an instrumental variable must satisfy is the exclusion restriction. This is that the causal effect of the instrument z on y is fully mediated by the treatment t. Z doesn't satisfy the exclusion restriction in this graph because of this direct edge from z to y. It doesn't go through t. So to satisfy the exclusion restriction assumption, we must have a graph where that edge is removed. Recall that when we saw these probabilistic graphical models in week 3, that we saw that removing edges corresponds to adding assumptions. Right here we're saying that we're restricting the data generating process so that we're excluding Z from the causal mechanism that generates Y. So this means that whenever we have variation in Z, it's going to go through T, the thing that we want to know the effect of on Y. If variation in Z were to go directly to Y, then we wouldn't be able to isolate the causal effect of T on Y using this Z. Then the third assumption for Z to be an instrument is what we'll call instrumental unconfoundedness. That means that the effect of Z on Y is unconfounded. In other words, there are no unblockable backdoor paths to Y. So in this graph, we see that we have a backdoor path from Z to Y, which is Z to U to Y. And because U is unobserved, we can't block that backdoor path. So we don't have instrumental unconfoundedness in this graph. We have to remove more edges to get instrumental unconfoundedness. So if we remove this Z to U edge, then we have instrumental unconfoundedness satisfied. Just like the assumption in the last slide, this assumption corresponds to removing an edge from the graph. And we could have a graph where there is a backdoor path from Z to Y, so here it's Z to W to Y, but because W is observed, we can block that backdoor path by conditioning on it. This gives us a slightly weaker version of the assumption 3, where we have unconfoundedness after conditioning on observed variables. And if we have this, we would call Z a conditional instrument. That concludes this section of the lecture and brings us to the following question. What are the 3 assumptions that we need to say that a given variable is an instrument, and what do they correspond to graphically? We'll now move on to the section where we emphasize that we can't get nonparametric identification of the ATE using instrumental variables. So why didn't we see instruments in week 5 when we were looking at identification? Well, the answer is that week 5 was about nonparametric identification, where we don't make any assumptions about the structural equations or the causal mechanisms that generate the variables. So if you recall, in that week we saw a necessary condition for nonparametric identification, and that necessary condition was, for each backdoor path from T to any child that is an ancestor of Y, it is possible to block that path. So in this graph, just consider that Y is an ancestor of itself. And here in this graph, Y is a child of T, but we can't block this backdoor path for U because U is unobserved. Therefore, this necessary condition tells us that we can't get nonparametric identification in this case. We're going to have to make some assumptions about the parametric form for the structural equations that generate some of these variables. So, for example, instruments might look a bit similar to the mediators in the front door criterion, but we don't have nonparametric identification when we have an instrument, whereas we do have nonparametric identification when we have the front door criterion satisfied. So while we can't get identification if we don't make any assumptions about the parametric form of the structural equations, we can fairly easily show that we can get identification if we have that the structural equation for the outcome Y is linear. So we'll use that linear setting as a warm-up now. If we make this assumption that the outcome is a linear function of T and the unobserved confounder U, then we can get identification. So this is a 4th assumption, and unlike the 3 assumptions before, this assumption is about parametric form. And importantly, in this structural equation, Z doesn't appear. That's because of the exclusion restriction assumption. Z isn't a parent of Y, so it's not part of the causal mechanism that generates Y, and this causal mechanism here we're assuming is linear in this slide. That's the assumption we're introducing in this slide. We'll start in the setting where Z and T are binary, and because our goal is to identify the causal effect of T on Y, and because we know that this instrument Z is supposed to be useful somehow, we'll start with this quantity, the expected value of y given z equals 1 minus the expected value of y given z equals 0. So we're starting with this associational difference, and we're going to use it to show that we can identify the causal effect of t on y, which in this case is just delta because that is the scalar in front of t in the linear structural equation that generates y. You can see that structural equation in the bottom right corner of the screen. And the very first thing we're going to do is just plug that structural equation in for y, so that's what we get here. To do this, we're using the linear outcome assumption, and in addition, we're using the exclusion restriction assumption since that tells us that z doesn't show up in this structural equation for y. Then we can just use linearity of expectation and regroup terms so that we have the delta terms grouped on the left and the alpha sub u terms grouped on the right. Then in these conditional expectations for u, we can get rid of z because u and z are independent due to the instrumental unconfoundedness assumption. You can see this independence in the causal graph in the bottom right here as u to t to z, that path is blocked by the collider t, and similarly any other path, so the other path from u to z would be u to y to t to z, is blocked by the collider y. So because of that independence between u and z, we could just remove the z that was behind the conditioning bar in the conditional expectation for u. Then expected value of u minus expected value of u is 0, so we can just remove that term. And finally, we can solve for delta by just dividing both sides by this factor here to get this equation. The right-hand side is purely statistical, as there's no potential outcomes or do operators, so you know that we've identified the causal effect delta, which in the linear setting is the average treatment effect, and it's the individual treatment effect for every individual as well. But there's one more thing, which is what if the denominator is 0? Then we would have something that's undefined. And that's what the one assumption that we haven't used yet gives us. That's the relevance assumption. That was the very first one that we saw. That assumption tells us that this denominator must be non-zero. So using all of those four assumptions, we've identified delta. The linear setting can give us some useful intuition for instrumental variables, as the causal association that flows along a directed path in linear setting is just the product of coefficients along that path, where the coefficients on these edges denote the coefficients that are in front of the parent on the edge in the structural equation that generates the child. So delta is in front of t in the structural equation for y, and alpha z is in front of z in the structural equation for t. Okay, so we're going to multiply some coefficients along these paths and show how that gives us intuition for instrumental variables. So the first is to look at the numerator of this identifying equation for delta here. In the numerator, we have the causal effect of z on y. So we can see that graphically as this z to t to y path. To get that, we multiply the alpha sub z coefficient times delta, and we just put that in for the numerator. And then similarly, the denominator is the causal effect of z on t. So we do that by just looking at the edge from z to t. Because this path consists of just one edge, this causal effect of z on t in the denominator just turns into that coefficient on just that edge. And then we can see that the alpha sub z's cancel out to give us delta. So the way we're identifying the causal effect here is we're first identifying the causal effect of z on y, which we can get because there's no confounding of the effect of z on y. There's no backdoor paths from z to y. And then we're identifying the causal effect of z on t here, and then we're just dividing that. So we're just getting this path and then canceling out this part to leave us with the effect of t on y. All right, so that's some useful intuition. How do we actually estimate this quantity? This specific estimand on the right-hand side is known as the walled estimand. And because this estimand consists of just 4 different expectations, the walled estimator is easy enough. To estimate the expected value of y given z equals 1, we just look at all of the samples where z equals 1, and then we average over them. So we just average over y, and n1 is the number of examples where z equals 1. Then we do the same for the other conditional expectations. N0 here is the number of samples where z equals 0. And in the denominator, we're just doing the same thing for t, since it's an expectation over t. So we just saw how to identify the causal effect of t on y using the instrument z in the binary setting where z and t are binary. But what if t and z are continuous? Can we still identify the causal effect of t on y in that setting? Yeah, if the structural equation for y is still linear, then we can identify the causal effect. It ends up just being the covariance of y and z divided by the covariance of t and z. So I put these two estimands next to each other. On the left-hand side, there's the one in the binary setting. On the right-hand side, there's the one in the continuous setting. I put these next to each other because they're very similar. You might think of the one on the right as the continuous analog of the one on the left. And we'll now actually derive the one on the right. Just as in the binary setting, z and y are kind of special, as z is the instrument that we want to use for identification, and y is the outcome that we're interested in for measuring the causal effect of t on. So it seems like something useful that we might want to start with is the covariance of y and z. The first step we'll use is apply a basic covariance identity. You can look this up on Wikipedia if this looks unfamiliar. Then we just plug in the structural equation for y, just as we did last time. Here we're using the linear outcome assumption and the exclusion restriction assumption, same as last time in the binary setting. You'll see that many of the steps in this proof parallel the ones in the binary setting. Then if we just distribute terms and apply linearity of expectation, we get this. And then we can rearrange terms to bring the delta terms together and the alpha terms together. This allows us to easily see that we can now apply the same covariance identity that we used in the very first step. We can now apply that twice here to get the covariance of t and z and the covariance of u and z. Then u and z are independent by the instrumental unconfoundedness assumption, so that covariance is 0, so we can remove that term. And finally, we can just solve for delta, where the denominator here is non-zero due to the relevance assumption, so this is not undefined. So we've identified the causal effect of t on y in the setting where z and t are continuous now. Then we can use this estimand for estimation by just plugging in estimates of each of these covariances. That gives us an estimate for delta. This is analogous to the walled estimator. But another estimator that we could use here, which is more useful for giving us intuition about why instruments work, and which happens to also be a very popular estimator, is known as the two-stage least squares estimator. So what does that estimator look like? It's two stages. The first is that we linearly regress t on z to estimate the conditional expectation of t given z. This gives us a projection of t onto z, which we'll label as t hat. It's the best predictions in the mean squared error sense that we can get for t, given that we are using z as input. And then we'll use that t hat in the second stage, where we linearly regress y on t hat to estimate the conditional expectation y given t hat. And our estimate for delta will be the fitted coefficient in front of t hat in that linear regression. So here's the intuition that I mentioned this estimator is useful for. Consider this graph in the bottom here, and consider that t hat equals the estimated expectation of t given z. Imagine that we change this graph, so instead of using t, we're going to use t hat. Right, so in stage 2 of the estimator, we're not regressing y on t, we're regressing y on t hat. And then note that t hat is only a function of z, it's not also a function of u like t is. So because t hat isn't a function of u, we can remove this edge from u to t hat. And that shows you why, if we use t hat instead of t, we remove confounding here, right? There's no unobserved confounding from t hat to y. There's no backdoor paths from t hat to y. That's because we kind of removed that unobserved confounding when we projected t onto z to get t hat in stage 1, which we then used in stage 2 to regress y onto t hat. And this two-stage least squares estimator is really popular. You can also use it in the binary setting. Z and t don't have to be continuous to use it. And that's the end of this section. Here's the proof that we saw in the binary setting again. And the question here is, where do we use each of the 4 assumptions in the proof below? Then the next question is for the continuous linear setting. In the continuous linear setting, prove that delta is equal to the covariance of y and z divided by the covariance of t and z. We just saw that we can get identification if we make a linear parametric assumption, but it's much more attractive to get nonparametric identification. And that's what we'll do in this section, where we'll nonparametrically identify a slightly different estimate known as the local average treatment effect. Keep in mind that we can't nonparametrically identify the regular average treatment effect, as we saw in section 2 of this lecture. To give you a bit more motivation for why we're not satisfied with the identification we got in the last section, where we made this linear outcome assumption, it's worth emphasizing that by making this linear outcome assumption, we are assuming that all individuals, all units, have the exact same treatment effect, delta. In other words, the treatment effect doesn't vary across units. It's completely homogeneous. And there's a few different variants for homogeneity assumptions. You can see more in section 16.3 of the Hernan and Robbins book. We used one specific one, this linear outcome assumption. Anyway, the point is that assuming that the causal effect is the same for everyone is very restricting. It's something that we shouldn't be satisfied with in most scenarios. So the question you should have in your mind now is, can we get identification without parametric assumptions? Specifically talking about identification using instrumental variables in the presence of unobserved confoundings here. As you might have guessed by the title of this section, the answer is yes. And to do this, we have to introduce a few new things. We have to introduce some new notation and some new concepts before we can get to the proof. Some hopefully familiar notation is that y1 and y0 are the 2 potential outcomes. One is the potential outcome that you would receive under treatment, the other is potential outcome you would receive under no treatment. And these are short for y t equals 1 and y t equals 0. Now that we have an instrument z, we can talk about those for the treatment as well. So we'll have t when you intervene on z to set it equal to 1, and t z equals 0 when you intervene on z to set it equals 0. And similarly, we'll use t1 and t0 as shorthand for that. So rather than potential outcomes, you could think of these as potential treatments. Potential treatment under instrument equals 1 and potential treatment under instrument equals 0. Just as we have the fundamental problem of causal inference for potential outcomes, we would have the fundamental problem of causal inference for potential treatments. And we can also talk about why when we intervene to set z equals 1 and y z equals 0. So those are like potential outcomes, but the thing that we're intervening on isn't treatment, it's the instrument. We won't use any shorthand for that. We'll always use y and then in parentheses z equals whatever value. Okay, so that's some important new notation that we'll need, and then we can now use that to define a new concept that we'll need, which is the concept of principal strata. Basically, we're going to break the data into 4 different strata or groups based on how the instrument affects the treatment that people in that group take. So basically, we're breaking people into groups based on this arrow from z to t. And there's going to be 4 different groups rather than just one group, because t is not just generated from z, but it's also generated from u. So depending on the value that each unit takes for u, it will be put in a different group, one of these 4 groups. The first group is known as compliers. Those are the people who, when they get instrument equals 1, then they take treatment t equals 1. And when they get instrument equals 0, they take treatment t equals 0. So you can think of Z as the assignment, or what people are encouraged to take. So if you are assigned treatment 1, so that's Z equals 1. You're being encouraged to take treatment equals 1. Or if you are encouraged to take treatment equals 0, that corresponds to Z equals 0. And the compliers are the ones that they just take the treatment that they are encouraged to take. They're complying with their assignment, Z, when they decide their values of treatment, T. That's one of the groups. And then another are the defiers. These are the ones that are always going to take the opposite treatment that they are encouraged to take. So if Z equals 1, they're going to take treatment 0. If Z equals 0, they're going to take treatment 1. Right, so these are really consistent contrarians. For example, the defiers group could be a bunch of defiant teenagers. It could be composed of a bunch of people like that person you know who always takes the opposite position of you, no matter what the position you take is. So that's the defiers. Then the next principal stratum is the group of always takers. These are people who are always going to take the treatment. They're always going to have t equals 1, no matter what Z is. No matter what they're encouraged to do. If they're encouraged to do 0, so if they get Z equals 0, they still will take t equals 1. And finally, we have the never takers, who are people who always have t equals 0. An important thing to note is that you can't identify which stratum a person is in based on their observed values of instrument and treatment. So, for example, say they got Z equals 1 and T equals 1, you might think, oh, maybe they're the compliers, but also they could be the always takers. Similarly, say they got T equals 0 and Z equals 0, you could think they're the compliers, but they could also be the never takers. Or if they got Z equals 1 and then T equals 0, they could be the defiers, but they could also be the never takers. Or if they got Z equals 0 and T equals 1, they could be the defiers, or they could be the always takers. So for any combination of Z and T that you observe, you could be in any of two groups. You can't identify which group you're in, just from the observational data. This is related to the fundamental problem of causal inference, but for the instrument-treatment relationship rather than the treatment-outcome relationship. And in the causal graph we have on the slide, we have an edge from Z to T. However, that's not the case for all of these different groups. We could draw a different graph for each group. And the graph we have right here is basically just the graph that's a union of all those different graphs' edges. So specifically for the always takers, no matter what Z is, if Z is 1 or if Z equals 0, T is always going to be equal to 1. In other words, Z has no effect on T in the always takers. So there's really no arrow from Z to T in the always takers group. And it's the same with the never takers, because for them, no matter if Z equals 1 or if Z equals 0, they're going to take T equals 0 in both cases. So for both the always takers and the never takers, their graphs don't have any edge from Z to T. There is no causal effect of Z on T in those groups. This is something crucial that we'll be using for identification of the local average treatment effect. But before that, we have one last thing to do, which is introduce the monotonicity assumption. This is the assumption that for every individual I, the value of treatment that they would take, given that they are given encouragement, Z equals 1, is greater than or equal to the value of treatment that they would take if they were not given encouragement, Z equals 0. So in the causal graph, this assumption is making an assumption about the relationship of Z and T. We're assuming something specific about this edge from Z to T. And specifically, that means that in these groups, we are eliminating the defiers group. This is because in that group, when z equals 1, you get 0, which is a smaller value than when z equals 0, which t will then be 1. So 0 is smaller than 1, which violates this greater than or equal assumption here, unlike with the compliers where 1 is greater than 0, and the always takers, never takers, where you have the equal sign. So 1 equals 1, so it doesn't violate greater than or equal to, and 0 equals 0, so it doesn't violate greater than or equal to. So that's why by making the monotonicity assumption, we are getting rid of the defiers group. We are assuming that there are no defiers. With all of that out of the way, we're finally ready to nonparametrically identify the local average treatment effect, and we'll be doing that derivation on this slide. Just as in the two linear examples before, we're going to consider the relationship between y and z and start with that for our derivation. So we'll be looking at the expected difference in y when we take encouragement z equals 1 and y when we take z equals 0. The first thing we'll do is condition on and marginalize out the different principal strata. So in all of these four terms, we just have what we started with, this expected difference, and we've conditioned on being a complier here, being a defier here, being an always taker, and being a never taker, and then we're just multiplying the probability of being in that stratum. So this is just the law of total probability. Then we know that the probability of being a defier is 0 by the monotonicity assumption, since that tells us that there are no defiers. So because that's 0, we can just get rid of this whole term, the defiers term. Then consider the causal effect in the always takers and never takers groups. So the causal effect of z on y is actually going to be 0 in those groups. Remember that there was no edge from z to t in those groups, and that's because t is going to be independent of z. That's what's in these parentheses here. So in the always takers, t equals 1 regardless of what z is, and in the never takers, t equals 0 regardless of what z is. So that's going to mean that these causal effects are 0. So we can get rid of those terms as well. This means that we're only left with the compliers term. If we then just solve for this conditional effect, so we divide both sides by this probability, then we get the conditional effect here, and what we started with in the numerator, and then this probability in the denominator. Because we're conditioning on being a complier here, we know that z equals 1 is the same as t equals 1, and z equals 0 is the same as t equals 0 because they're compliers. So we can just plug those in right here. And now it looks like we're looking at a treatment effect, the effect of t on y. So we'll call this the local average treatment effect or complier average causal effect. See, let's take complier average causal effect first. We're looking at the complier average causal effect because we're conditioning on being a complier. And then we're looking at the average causal effect in that group. It's like a local average treatment effect because it's local to this specific stratum, the complier stratum, rather than being an average treatment effect over the whole population, over the global population. Okay, then if we look at the numerator here, where we have y where z equals 1, y where we've set z equals to 0, we can actually turn this into just simple difference in conditional expectation, so just the associational difference. This is because of the instrumental unconfoundedness assumption. We've assumed that the causal effect of z, the instrument z, on our outcome y is unconfounded. That's just in the definition of an instrument. And then for this denominator here, we're going to take it to its own little box to see what that turns into. So this is the probability of being a complier. And another way we can write the probability of being a complier is as 1 minus the probability of not being a complier. To write that, we need to know what the probability of not being a complier is. And because we've broken things down into 4 different strata, we can just write the probabilities of those strata. So we need to write down the probability of being an always taker, the probability of being a never taker, and because we have the monotonicity assumption, we know that the probability of being a defier is 0, so we don't need to factor that in. Okay, so doing that, we get the following. This equation is saying that the probability of being a complier is equal to 1 minus the probability of not being a complier. And specifically, we have the probability of being a never taker here. So that's given that you were told to take the treatment, then you decided not to take the treatment. You took t equals 0. But I thought we just learned that you can't identify the never takers or any of the groups from just the observational data. Here we just have an observational distribution. There's no potential outcomes, no potential treatments in this term. So why were we able to write down the probability of being a never taker with purely statistical language, with just the observational distribution? Well, it's because we made the monotonicity assumption, also known as the no defiers assumption. People who fall into this probability could have been either never takers because they didn't take treatment, or they could have been defiers because they defied the z equals 1 encouragement. But because there's no defiers, we know that this probability actually just corresponds to the never takers. And similarly, for this probability, for the always takers, this probability could have corresponded to people who were either always takers because they have t equals 1, or people who were defiers because the t doesn't match the z here. But we know that it's actually just the probability for the always takers because we've assumed away defiers. Okay, so the monotonicity assumption is doing a lot of work for us in this derivation right now. We saw that it helped us get rid of defiers up above, right up here when we crossed out this term. And now it's giving us this equality. It's letting us write this probability of compliers in terms of purely observational distribution. In other words, the monotonicity assumption allows us to identify the probability of compliers, something which we wouldn't normally be able to identify because, as we discussed in previous slides, you can't identify the principal strata that people are in without assumptions. Okay, so I just thought it would be worth emphasizing how important the monotonicity assumption is there. And now we can just continue on with the derivation. This p of t equals 0 given z equals 1 is the same as 1 minus p of t equals 1 given z equals 1. And then the 1's cancel and you end up with a positive p of t equals 1 given z equals 1. Because we're in the setting where t is binary, the probability of treatment equals 1 is actually equal to the expected value of treatment. So we can write this difference in conditional probabilities as this difference in conditional expectations. And finally, we can plug in what we've just derived in this box back into what we were deriving before in the denominator there for the end of our derivation. We end up with the fact that the local average treatment effect, or complier average causal effect, is equal to the difference in conditional expectations in y given z divided by the difference in conditional expectations in t given z. So it's like the association between y and z divided by the association between t and z, which should seem familiar to you. Okay, so let's get rid of all this derivation and just write the result. That's what we have in this equation here. We have the local average treatment effect, or late, on the left-hand side, and the result that we just got on the right-hand side. And this causal estimand that we've identified is the causal effect in the complier group. So it's not quite the causal effect in the global population. That's what the ATE would be. So for contrast, here's the ATE right below it, where we're not conditioning on being compliers. That's this part here in the late causal estimand. And then the statistical estimand that we ended up with is just the walled estimand. this is the thing we derived in the really simple warm-up in the beginning, where we were in the binary z and t linear setting. But here we derived it in a completely non-parametric setting. There was no linear or homogeneity assumption. The difference is that when we made that linearity or homogeneity parametric assumption, we were able to identify the average treatment effect. Whereas now, when we don't make that assumption, but we do still make another assumption, the monotonicity assumption, we're able to identify the local average treatment effect, also known as the complier average causal effect. So we're able to identify a different estimand. But what's really cool is this was nonparametric identification, and we still end up with this simple walled estimand. There are some problems with late though, namely the monotonicity assumption isn't always satisfied, right? So you might be in a setting where encouragement, where with your instrument, isn't always going to positively or non-negatively affect the treatment that they take, right? It's not going to always make them take the treatment that they were encouraged to take or take the treatment that they were going to take regardless. That's when it's equal to 0. Okay, so the potential violation of monotonicity is one problem. And then another is that even if we do have monotonicity, even if it is satisfied, we are usually interested in the average causal effect across the whole population, rather than just in the compliers. And this is partially because we don't even know who the compliers are. We can't identify who is a complier, even given the monotonicity assumption. So if we can't identify who the compliers are, then we're not exactly sure who the complier average causal effect is referring to, right? So who in the population, the walled estimand that we're estimating, who that ends up accurately describing their causal effect. But there's still a lot of literature on estimating local average treatment effects, so it's something that people definitely do care about. These are just some problems with it. That concludes this section of nonparametric identification of late. And the question that we'll ask is, what causal estimand can we nonparametrically identify with an instrument and the monotonicity assumption? So we've seen identification of the average treatment effect under linearity assumptions, and we'll now look at identification of the ATE in more general settings, relaxing the linearity assumption. In the first class of methods, they let us model the structural equation for y as some very flexible function of treatment and observed confounders, plus some additive unobserved noise. So the really important assumption here is that the noise is additive. We don't have a function f where the arguments are t, w, and u. Rather, u only enters into the structural equation for y additively. And there's a bunch of different papers where they use different kinds of f's here. One is where you use deep neural networks. You can check out these references. Other common approaches are to use kernel methods for f. So the general idea is that once you add this additive noise assumption, and once you've chosen your model class f, which could be what people consider nonparametric, then you get identification of the regular average treatment effect, not the local average treatment effect. Because these methods make this additive noise assumption, they're really semi-parametric. So even if this f part is non-parametric, they're adding this parametric assumption, the additive noise one, which makes it the whole thing semi-parametric. Another option is to give up on point estimation of the average treatment effect using instruments, and instead try to do set identification. In other words, get a upper and lower bound for the average treatment effect. One of the main resources to check out for that is section 8.2 of Pearl's causality book. And giving up on point identification and focusing more on set identification can allow us to relax, for example, the additive noise assumption that we saw on the previous slide. So here we have the outcome for y, the structural equation for y is f of t, where f is whatever, plus some additive noise. That's what we saw on the previous slide, minus the observed covariates w for simplicity. Then if you're not worried about point identification, what you can do is move the u that entered additively before inside of the function f so that you're relaxing that additive noise assumption. Go ahead and check out this paper and references in it for how to do set identification, how to get bounds on the average treatment effect using these more flexible instrumental variable methods. And that concludes the instrumental variables lecture. Go ahead and hit a thumbs up down below if you like this lecture, and make sure to hit subscribe in the bell icon if you want to get notifications for future videos. Thanks for watching, and I hope to see you in the next one.